A car accelerates from rest, so that right away tells us what? Tells us that VI is equal to 0 at a rate of 4 meters per second squared. That's our acceleration, 4 meters per second squared, for 3 seconds. How far did the car travel? It's a nice thing about physics and math. All of these words boil down to a few simple givens and then an equation. And frankly, it doesn't matter whether it's a car, a jet, a person. We just care about the numbers. So in this case, it's a car. I'll put a hood on the car this time. And it's at rest, so there's no velocity here. And over here, we don't know. We're not asking for that, are we? Yes, we are. We're asking for how far it goes. Okay? We're not asking for its final velocity. We want to know how far it goes. And it has 3 seconds of acceleration of 4 meters per second squared. So we look for what formulas we can use. In this case, it's the second kinematics equation. When you're looking for displacement, that's the ticket. The first one will give a first kinematics equation gives a final velocity. The second gives us a displacement. Fortunately, it's already in the correct form. We don't have to manipulate it. So we start with delta x is v sub I t. So what is our initial velocity? Well, it's 0, okay? So this term doesn't even show up. All we have is 1/2. The rate is 4 meters per second squared times the time squared. So 3 seconds squared. Be careful about this too. The most common error in the second kinematics equation is people forget to square that term. So we're not going to forget. And 1/2 of 4 is what? 2. Then 3 squared is 9. 2 times 9, 18. And what happens to the units here? Okay, we have meters per second squared here. We have seconds squared here, right? Because we squared it. That cancels out. We're left with meters. Our answer is 18 meters. Delta x is equal to 18 meters. And then let's pull out the answer tab to make sure. Yep, that's what we got, 18 meters.